100,000 galaxies are moving through the universe right now towards something so massive that its gravity reaches across 200 million light-years of space. This is not a distant phenomenon happening somewhere far away from us, but rather a journey we are taking together at this very moment as you listen. The Milky Way, our home galaxy containing every star you have ever seen in the night sky, travels through intergalactic space at 600 kilometers per second. We are passengers on this cosmic voyage, carried along with everything around us toward a destination we cannot directly see with our most powerful telescopes. The motion happens in perfect silence, without any sensation of movement, the way a passenger on a vast ship might not feel the vessel crossing calm waters. Nothing in your daily experience reveals this journey. No stars shifting perceptibly in the sky, no sense of rushing through the void between galaxies at speeds almost impossible to comprehend. Yet, the motion is real, measured precisely by astronomers who detected the subtle fingerprints it leaves on light arriving from distant corners of the cosmos. We have been traveling toward this destination since before the Earth existed, and we will continue traveling toward it long after the sun has exhausted its fuel. You are listening to the Drowsy Astronaut, and tonight we drift together through one of the most remarkable mysteries the universe has offered to human understanding. This is a slow journey meant for late nights when curiosity and rest can share the same quiet space without either demanding too much of the other. If you enjoy these slow voyages through the cosmos, consider sharing where you are listening from tonight in the comments below. Perhaps leaving a like or subscribe to help others find this place. Now settle in, get comfortable, and let us move deeper into this hidden force at the heart of our cosmic neighborhood. The speed of our motion toward this unseen destination almost defies everyday understanding. 600 kilometers passing beneath us every single second of every day and night. That means roughly 20 million kilometers traveled by the time a single Earth day completes itself. Yet even at this pace, the destination remains impossibly distant ahead. The galaxies around us participate in the same flow. Andromeda and the Magellanic Clouds and dozens of smaller companion galaxies, all caught in the same gravitational current. We are not alone in this journey, but rather part of an enormous cosmic river, carrying everything in our region of space toward whatever waits, beyond our ability to see. The source of this gravitational pull has been given a name that captures both its power and its mystery, a name that speaks to the way it draws everything toward itself. Astronomers call it the Great Attractor, a term first used in 1986 when the evidence for this vast motion became impossible to explain through any ordinary cause. The name suggests something actively pulling, something reaching out across the emptiness to gather galaxies into its gravitational embrace over timescales measured in billions of years. What exactly constitutes the Great Attractor remained unclear for decades after its discovery, the source hidden behind obstacles that prevented direct observation. The distance to the Great Attractor measures roughly 150 to 250 million light-years, depending on exactly which concentration of mass you identify as the primary source of attraction. Light leaving that region when the earliest dinosaurs walked the Earth is only now arriving at our telescopes. carrying ancient information about structures that have continued evolving during the intervening ages. The journey we are taking will require billions more years to bring us appreciably closer to this destination. The distances involved, so vast that even our remarkable speed barely makes progress. The universe operates on timescales that make human civilizations seem like brief flickers in an endless night. Our galaxy participates in this flow, along with an enormous number of companions, the estimate of 100,000 galaxies, representing only those we can observe and count within the affected region. Each of these galaxies contains billions or hundreds of billions of stars, each star potentially hosting planets of its own, all of them carried together toward the same gravitational center. The flow extends across a volume of space so large that light itself requires hundreds of millions of years to cross from one edge to the other. We occupy one small corner of this vast cosmic watershed, participating in a journey that connects us to structures almost incomprehensibly larger than our home galaxy. The motion we are experiencing is not the ordinary expansion of the universe that carries all galaxies apart from each other, as space itself stretches over cosmic time. This is something additional, a peculiar velocity superimposed on top of the expansion, a component of our motion that points in a specific direction rather than following the general cosmic flow. Imagine floating on a river that is itself moving through a larger landscape, the expansion of the universe providing the background current, while the Great Attractor adds a directed pull toward one particular shore. We are caught in both motions simultaneously, expanding away from distant galaxies, while falling toward the massive concentration that defines our local gravitational neighborhood. The pull has been operating since the early universe, since the first structures formed from the nearly uniform distribution of matter that existed shortly after the beginning of everything. Gravity works slowly but relentlessly, the tiniest concentrations of mass, attracting more material over millions and billions of years, growing gradually into the enormous structures that now dominate the cosmic landscape. The Great Attractor represents one such concentration, a place where matter accumulated more densely than average in the early universe and then continued growing through the patient work of gravitational attraction. We are feeling the influence of a structure that began forming perhaps 13 billion years ago when the universe was still young. The experience of this motion remains entirely hidden from human perception. No force pressing you backward in your chair, no sensation of acceleration or velocity relative to the cosmic reference frame. The smoothness of the journey results from the gentleness of gravitational gradients across the enormous distances involved. The pull varying so slightly from one side of the Milky Way to the other that nothing experiences differential force. We are falling freely through space, weightless in the cosmic sense, even as we perceive gravity from nearby masses like the Earth beneath us, and the Sun anchoring our orbit. The cosmic motion occurs at a scale so vast that it becomes invisible to creatures our size, living on timescales measured in decades. The direction of our travel points toward a region of sky in the southern hemisphere, toward the constellations Centaurus and Hydra, as seen from Earth on clear, dark nights. Looking in that direction, we might expect to see something remarkable, some obvious concentration of light that would reveal the source of all this gravitational influence pulling us through space. Instead, We see the plane of our own galaxy, the thick band of stars and dust that comprises the Milky Way's disk, blocking our view of whatever lies beyond. The Great Attractor hides behind our own galaxy, obscured by the very stars and dust that make our home so beautiful when viewed from within. This obstruction represents one of the great frustrations and mysteries that defined the early study of the Great Attractor. The source of the pull remaining invisible precisely because we needed to look through the most obscured region of our sky to find it. Astronomers could detect the motion clearly, could map the flow of galaxies toward a common destination, but could not simply point a telescope at that destination and photograph what was doing the pulling. The universe seemed to be playing a cosmic joke, placing the most important gravitational influence on our local region of space, directly behind a wall of stars we could not see through. This challenge would drive decades of innovative observation, as astronomers sought ways to peer beyond the veil. The journey we are taking together tonight will explore how this mystery unfolded, how the hidden motion was first detected, and how patient observation eventually revealed what lay beyond our galaxy's obscuring disk. We will visit the massive structures that contribute to the gravitational pull, the galaxy clusters and superclusters that define our cosmic neighborhood at the largest scales. The voyage will carry us through invisible matter that provides most of the gravitational attraction, through the cosmic web that connects everything, and eventually back to this moment where we rest while traveling faster than any vehicle humans have ever built. The universe moves through itself, carrying us along, and the story of how we discovered this hidden journey reveals something beautiful about human curiosity. The motion continues as you listen, 600 kilometers passing in the second it takes to hear a single word. Yet, nothing changes in the apparent positions of the stars above your location tonight. The smoothness of this cosmic travel allows life to proceed uninterrupted, allows planets to orbit their stars and moons to orbit their planets, without perturbation from the vast journey underlying everything. We are embedded in a flow that connects us to the largest structures in the observable universe, participants in something far grander than our everyday experience suggests. The Great Attractor waits in the distance, patient and invisible, drawing everything toward itself through gravity that has shaped the cosmos since its earliest moments. The discovery of our hidden motion through space emerged from careful measurements of light arriving from galaxies scattered across the sky, in every direction we could observe. Astronomers in the 1970s and 80s noticed something strange in these measurements, a pattern that could not be explained by the simple expansion of the universe alone. Galaxies in certain directions appeared slightly different than galaxies in other directions, their light carrying subtle signatures of motion that revealed a flow toward one particular region of the cosmos. This asymmetry in the light became the first evidence that something massive and invisible was pulling our entire region of space toward itself. The signature astronomers detected involves the way motion affects the color of light through an effect most people have experienced with sound, but that applies equally to electromagnetic radiation. When an ambulance approaches, its siren sounds higher in pitch than when it recedes, the sound waves compressed or stretched by the motion of the source relative to the listener. Light behaves similarly, shifting toward blue when the source approaches, and toward red when the source recedes, a cosmic fingerprint of motion impressed upon every photon traveling through the universe. Astronomers reading this fingerprint in the light from distant galaxies found that something was causing a consistent pattern across enormous regions of the sky. The pattern they discovered showed galaxies in the direction of the southern constellations Centaurus and Hydra, appearing slightly bluer than expected. Their light shifted toward shorter wavelengths by the motion of our galaxy toward them. Galaxies in the opposite direction of the sky appeared slightly redder than expected, their light stretched by our motion away from them as we traveled toward the other side of the cosmos. This dipole pattern, brighter on one side and dimmer on the other, pointed like a compass needle toward whatever was causing our entire region of space to flow in one particular direction. The source of this flow remained mysterious, hidden somewhere in the direction the cosmic needle indicated. A team of astronomers, who would become known as the Seven Samurai, conducted some of the most important early work mapping this cosmic flow and estimating the properties of whatever was causing it. They measured the peculiar velocities of galaxies across a large volume of space, separating the component of motion caused by universal expansion from the additional motion caused by local gravitational influences. Their work revealed that the flow was not limited to our immediate neighborhood, but extended across hundreds of millions of light years, a vast river of galaxies, all streaming in the same general direction. The scale of this motion suggested something extraordinarily massive, serving as the gravitational source. The name Great Attractor emerged in 1986, when the evidence for this massive hidden source became compelling enough to warrant a dramatic designation. The name captured both the enormous gravitational influence required to produce the observed flow and the mystery of what exactly was doing the attracting. Estimates suggested that the source must contain mass equivalent to tens of thousands of typical galaxies, concentrated in a region perhaps 100 million light-years across, or less. This was not a single galaxy, or even a single cluster of galaxies, but something on an altogether larger scale, a concentration of matter that dominated the gravitational landscape across an enormous volume. The measurement techniques that revealed the Great Attractor required extraordinary precision and careful correction for all the other factors that can affect the apparent properties of distant galaxies. Astronomers needed to separate the redshift caused by the expansion of the universe from the additional velocity caused by gravitational attraction, a distinction that requires knowing the actual distance to each galaxy independently of its observed redshift. They developed methods using the relationship between a galaxy's size and its internal brightness to estimate distances, allowing them to identify which galaxies were moving faster or slower than expansion alone would predict. The accumulated data painted a picture of cosmic flow that pointed unmistakably toward a source in the direction of the southern sky. The challenge of studying this source became immediately apparent when astronomers tried to look directly toward the indicated region and see what was there. The Great Attractor's position in the sky placed it almost exactly behind the plane of the Milky Way, obscured by the dense band of stars and dust that makes our galaxy's disk so prominent in the night sky. Looking toward this region, telescopes saw only the foreground glow of our own galaxy, the distant structures hidden behind a veil that visible light could not penetrate. The Great Attractor had been detected through its effects on the motion of galaxies throughout a huge volume, yet remained invisible to direct observation. This situation represented something unusual in astronomy, where the evidence for a phenomenon typically includes direct observation of the object, causing the phenomenon, along with measurements of its effects. Here, astronomers had clear evidence of effects without any ability to directly see what was causing them, like watching objects on a table slide toward one edge, without being able to see what was pulling them. The invisibility resulted not from any property of the Great Attractor itself, but from our unfortunate position within a galaxy whose disk happened to block the relevant view. The universe had placed us in a cosmic blind spot relative to one of the most important gravitational influences on our region of space. The discovery generated significant attention both within the astronomical community and among the broader public. The idea of being pulled towards something invisible, capturing imagination, and inspiring attempts to understand what might be hiding behind our galaxy. Some early speculation suggested exotic possibilities, unknown forms of matter or concentrations of mass, unlike anything previously observed elsewhere in the cosmos. More conservative interpretations proposed that the Great Attractor was simply an unusually large collection of galaxy clusters, massive but not fundamentally different from other structures observed in unobscured regions of the sky. Resolving this question would require finding ways to see through the Milky Way's obscuring veil. The decades following the initial discovery brought gradual improvement in our understanding, as astronomers developed new techniques for penetrating the zone of avoidance, the band of sky where observations are most difficult due to our galaxy's intervening material. These techniques involved observing in wavelengths of light other than the visible spectrum that human eyes can detect, forms of electromagnetic radiation that interact differently with the dust and gas blocking our view. The patient accumulation of data from these alternative observations would eventually reveal the structures hidden behind our galaxy, transforming the Great Attractor from a purely theoretical construct into something we could actually map and characterize. The motion we detected through those early observations continues unchanged as you listen tonight. The Milky Way carrying us toward the same destination first identified almost 4 decades ago through the shifted colors of distant galaxies. Nothing about this journey has changed or will change on any timescale humans could experience. The flow as constant and patient as gravity itself, working across cosmic distances. The astronomers who first detected this motion understood that they had discovered something about our position in the universe, our embedding within a vast gravitational structure that connected us to masses far larger than anything in our immediate cosmic neighborhood. The Great Attractor remains ahead of us in the darkness, still exerting its pull across the light years. The story of detection reminds us that the universe often reveals itself through subtle effects rather than obvious displays. Patterns in data that only careful analysis can extract from the noise of observation. The astronomers who discovered our cosmic motion were reading the faintest of signatures in light that had traveled for millions of years before reaching their instruments, extracting information about structures so distant that their light predated humanity itself. This kind of patient detective work characterizes much of modern astronomy, where the most important discoveries emerge from meticulous measurement rather than dramatic single observations. The universe whispers its secrets to those willing to listen carefully. The band of the Milky Way, stretching across the night sky, represents one of the most beautiful sights available to human eyes. A river of light composed of billions of distant suns blended together into a continuous glow. This same beautiful band also creates one of the most frustrating obstacles in observational astronomy, blocking our view of roughly 20% of the entire sky, where the galaxy's disk intervenes between us and whatever lies beyond. Astronomers call this obscured region the Zone of Avoidance, a name that reflects the historical tendency to simply avoid observing in directions where the foreground confusion made meaningful observation nearly impossible. The Great Attractor happens to lie almost exactly in this zone, hidden by the very light that makes our galaxy so magnificent. The obstruction occurs because the disk of the Milky Way contains not only billions of stars, but also vast clouds of gas and microscopic dust particles that absorb and scatter visible light passing through them. Light from distant galaxies beyond our own must traverse these clouds on its journey toward Earth, losing intensity at each encounter with dust grains that block or redirect the photons from their original paths. The effect accumulates across the tens of thousands of light years that the light must travel through our galaxy's disk, dimming distant sources to the point of invisibility, even for the most powerful telescopes. The thickest part of this obscuring layer lies in the direction of the galactic center, precisely where the Great Attractor happens to be located from our perspective. The location of the Great Attractor behind the Zone of Avoidance resulted from pure cosmic coincidence. The geometry of our position within the Milky Way happening to place this important gravitational source in the worst possible direction for observation. Had we been located in a different part of our galaxy, or had the Milky Way been oriented differently, the Great Attractor might have been clearly visible as an obvious concentration of galaxies from the earliest days of extragalactic astronomy. Instead, generations of astronomers could only infer its existence from the motions it caused, unable to directly photograph the galaxy clusters that might compose it, or measure their properties through conventional means. The universe had given us clues about its hidden structure, while simultaneously blocking our ability to see that structure directly. The experience of looking toward the Zone of Avoidance differs dramatically from looking toward clearer regions of the sky, where the distant universe reveals itself in deep telescope images. In directions perpendicular to the Milky Way's disk, long exposures reveal thousands of galaxies scattered across each photograph. Island universes spanning billions of light years, visible in exquisite detail through the relatively empty space between us and them. In directions towards the galactic plane, the same telescopes see primarily stars from our own galaxy, the distant universe hidden behind a foreground that refuses to part. The contrast highlights how much our view of the cosmos depends on the particular circumstances of our location within our home galaxy. Some regions of the Zone of Avoidance are more opaque than others, the dust distribution varying with position along the galactic plane and creating pockets of relative clarity amid the general obscuration. These clearer windows have allowed occasional glimpses of structures beyond our galaxy, even in directions close to the plane, tantalizing hints of what a full survey might reveal if the obstruction could be overcome. The Great Attractor region includes some of these partial windows, though none clear enough to provide the comprehensive view that astronomers desired for mapping the source of the cosmic flow. The obstruction remained sufficient to frustrate conventional optical observation. Throughout the early decades of research into this phenomenon, the frustration extended beyond mere curiosity to practical problems in understanding the local structure of the universe, since the hidden region contained whatever was producing the dominant gravitational influence on our cosmic neighborhood. Imagine trying to understand the geography of a landscape while blind to whatever lay in one particular direction, knowing that something important existed there, but unable to determine its exact nature or extent. Astronomers mapping the distribution of galaxies throughout the nearby universe found themselves working with an incomplete picture. The Great Attractor region appearing as a blank zone in their maps, where data simply could not be obtained through ordinary means. This incompleteness limited progress in understanding why we were moving the way we were. The concept of the Zone of Avoidance predates the discovery of the Great Attractor by many decades, recognized as a problem since the early 20th century, when astronomers first began systematic surveys of galaxies beyond the Milky Way. Early catalogues of galaxies showed obvious gaps in the direction of the galactic plane, and initially, some astronomers wondered whether this represented a real absence of galaxies in those directions, or merely an observational limitation. The realization that our own galaxy was blocking the view came gradually as the nature of interstellar dust became better understood, transforming the apparent void from a mystery into an acknowledged blind spot. The discovery of the Great Attractor gave new importance to this old problem. The dust particles responsible for the obscuration are microscopic grains of carbon and silicon and other elements formed in the outer atmospheres of dying stars and distributed throughout the galaxy by stellar winds and supernova explosions. These tiny particles interact with visible light through both absorption and scattering, converting the light into heat energy or redirecting it away from the straight path toward Earth. The particles also emit their own light at longer wavelengths, glowing faintly in the infrared as they radiate away the energy they have absorbed from the starlight passing through them. This infrared emission would later become a key tool for penetrating the zone of avoidance. The gas accompanying the dust adds additional complications in some wavelengths, though its effects differ from those of the solid particles. Hydrogen gas, the most abundant element in the universe, absorbs and emits light at specific wavelengths that can be observed through radio telescopes, providing information about the structure of our galaxy that optical observations cannot match. Other gas species create their own spectral signatures, adding complexity to the foreground that must be understood and removed before distant sources can be studied. The zone of avoidance represents a multi-layered obstacle, each component affecting different types of observation in different ways. The challenge of the zone of avoidance forced astronomers to consider alternative approaches to observing the Great Attractor region, techniques that might penetrate the dust where visible light could not pass. The solution would come through the realization that electromagnetic radiation spans a vast spectrum of wavelengths, and that different portions of this spectrum interact differently with the intervening material that blocked our view. The same dust particles that completely block visible light might prove transparent to other forms of radiation, allowing distant galaxies to be detected through their emissions in these alternative wavelengths. This approach would eventually transform our understanding of what lay hidden behind our galaxy. The zone of avoidance persists today as a region of reduced observational access, though modern techniques have substantially mitigated its effects, compared to the situation in the decades immediately following the Great Attractor's discovery. Surveys in infrared and radio wavelengths have mapped thousands of previously unknown galaxies in directions that optical telescopes cannot effectively probe, filling in many of the blank regions on cosmic maps. The Great Attractor is no longer purely a theoretical construct, but something we can observe and characterize with reasonable confidence. Its nature revealed through patient application of technology designed to circumvent our unfortunate galactic position. Yet the zone remains a reminder of how much our view of the universe depends on where we happen to be within it. The key to seeing through our galaxy's obscuring veil lay in the realization that light exists in many forms beyond what human eyes can detect, and that dust interacts very differently with these various forms of electromagnetic radiation. Visible light represents only a tiny slice of the full electromagnetic spectrum, a narrow band of wavelengths that evolution happened to make accessible to our biological visual systems. On either side of this visible band stretch vast regions of the spectrum, from radio waves with wavelengths measured in meters to gamma rays with wavelengths smaller than atomic nuclei. The dust blocking our view of the Great Attractor proves nearly transparent to several of these alternative wavelengths. Infrared light carries slightly less energy than visible light and has slightly longer wavelengths, extending from the red edge of the visible spectrum into ranges our eyes cannot perceive but our instruments can detect. These longer wavelengths interact less strongly with the dust particles in our galaxy's disk, passing through the obscuring material far more easily than the shorter wavelengths of visible light. A cloud of dust that completely blocks visible light might transmit most of the infrared radiation passing through it, allowing telescopes sensitive to these wavelengths to detect sources that remain invisible to optical observation. The Great Attractor region, hidden behind the zone of avoidance to visible light, might reveal itself to infrared eyes. The development of sensitive infrared detectors throughout the late 20th century gradually made this approach practical for surveying large regions of the sky. Early infrared observations were limited by the sensitivity of available instruments and by the challenge of working at wavelengths where Earth's atmosphere itself absorbs much of the incoming radiation. Space-based telescopes eventually overcame the atmospheric problem, while steady improvements in detector technology increased the sensitivity and resolution of ground-based observations, where atmospheric windows permitted useful data collection. These advances would prove crucial for mapping the structures hidden behind our galaxy. One of the most important surveys for understanding the zone of avoidance was the 2-micron all-sky survey, often abbreviated as 2MAS, which mapped the entire sky at infrared wavelengths in the late 1990s. This survey detected the infrared glow of stars and galaxies across all directions, including regions of the zone of avoidance, where optical surveys found only obscuring dust. Galaxies that were completely invisible in visible light appeared clearly in the infrared images, their warm stars emitting radiation that passed through the intervening dust to reach the survey's detectors. The Great Attractor region began emerging from behind the veil. The infrared view of the zone of avoidance revealed a populated cosmos where optical astronomers had seen only emptiness. Thousands of previously unknown galaxies, appearing as the longer wavelengths, penetrated the dust that had hidden them. Some of these galaxies proved to be relatively nearby, their absence from earlier catalogues reflecting only the obstruction rather than any actual scarcity of galaxies in those directions. The distribution of galaxies behind the zone of avoidance could now be mapped for the first time, filling in the blank regions on cosmic maps and revealing structures that previous generations of astronomers could only infer from indirect evidence. The Great Attractor was becoming visible. Radio waves provided another window through the zone of avoidance. Their even longer wavelengths passing through dust, essentially without interaction. Radio telescopes had been observing emissions from hydrogen gas and other sources throughout the galaxy and beyond since the middle of the 20th century, though their application to mapping distant galaxy structures required specific techniques. Hydrogen gas emits a characteristic radio signal at a wavelength of 21 centimeters, and this emission can be detected from galaxies anywhere in the sky, regardless of the intervening dust. Surveys using this technique mapped thousands of galaxies through the zone of avoidance. The Parkes Radio Telescope in Australia contributed significantly to understanding the Great Attractor region, its location in the southern hemisphere providing good access to the relevant portion of the sky. Surveys conducted with this instrument detected radio emissions from hundreds of galaxies hidden behind our own, their hydrogen signatures revealing both their positions and their velocities relative to us. Combined with infrared observations, the radio data built an increasingly complete picture of what lay in the direction we were traveling, the hidden structures gradually revealing themselves through forms of light our eyes could not see. The veil was lifting. X-ray observations added another dimension to the picture, detecting the extremely high-energy radiation emitted by hot gas filling the space between galaxies in massive clusters. When galaxies gather into clusters, the gas between them heats to temperatures of millions of degrees, hot enough to emit X-rays that can be detected by telescopes orbiting above Earth's atmosphere, where these high-energy photons can reach the detectors. The Great Attractor region, if it contained massive galaxy clusters, should show up in X-ray surveys as bright concentrations of this hot gas. The observations confirmed the presence of significant mass concentrations in the expected directions. Each wavelength regime revealed different aspects of the hidden structures, the combination providing a far more complete picture than any single approach could achieve on its own. Infrared observations showed the stellar content of galaxies, the accumulated light from billions of stars that make up each galactic island. Radio observations traced the hydrogen gas that represents raw material for future star formation, and that traces the rotation and velocity of galaxies through Doppler effects. X-ray observations mapped the hot gas that fills massive clusters, providing estimates of the total mass required to heat and contain this diffuse material. Together, these approaches painted a portrait of the Great Attractor region. The portrait that emerged showed not a single massive object, but rather a complex region containing multiple galaxy clusters and superclusters spread across a vast volume of space. The gravitational attraction we experience results from the combined pull of all these structures, not from any single central mass, analogous to a star or black hole. This distributed nature of the Great Attractor made it harder to define precisely than a point-like source would have been, with different astronomers drawing different boundaries around what should count as part of the attracting region. The complexity matched what astronomers observed in other parts of the universe, where large-scale structure had been mapped without obstruction. The techniques developed to observe through the zone of avoidance continue improving with each generation of instruments, revealing finer details about the structures hidden behind our galaxy's disk. Modern surveys achieve resolution and sensitivity that would have seemed miraculous to the astronomers who first detected our cosmic motion through the shifted light of distant galaxies. The Great Attractor region is now mapped with sufficient detail to identify individual galaxy clusters and trace the flow of matter toward the gravitational centers that define our local cosmic neighborhood. The universe behind the veil has become accessible to scientific study. The experience of this revelation mirrors many episodes in the history of science, where patient, technological development eventually overcomes what once seemed permanent limitations on human knowledge. The astronomers who first detected the Great Attractor could only wonder what lay hidden in the direction they could not see, while modern researchers can examine high-resolution images of the same region taken at wavelengths that pass through the obstruction. The zone of avoidance remains a challenge, but no longer an insurmountable one, its secrets yielding gradually to the ingenuity of those determined to understand our place in the cosmic flow. The structures revealed by infrared and radio surveys included a massive concentration of galaxies that had been lurking just beyond our visual reach. A galaxy cluster now known as the Norma Cluster that appears to lie at or near the center of the Great Attractor. This cluster contains thousands of galaxies bound together by their mutual gravitational attraction, spanning a region perhaps 50 million light-years across, in the direction toward which our entire cosmic neighborhood is flowing. The discovery of the Norma Cluster provided the first concrete answer to the question of what exactly was doing the attracting, transforming an abstract gravitational concept into a visible collection of galaxies. The source of our cosmic motion finally had a face. The Norma Cluster carries the formal designation Abell 3627 in the catalogue of galaxy clusters compiled by George Abell and his collaborators. Though this clinical name hardly captures the significance of the structure for understanding our position in the universe. The cluster lies approximately 220 million light-years from the Milky Way in the direction of the constellation Norma in the southern sky, close enough to have been detected earlier, if not for its unfortunate position behind our galaxy's obscuring disk. At this distance, light leaving the cluster tonight will not arrive at Earth until long after our current civilization has transformed into something unrecognizable. The connection across such distances happens through gravity, not through light. The central regions of the Norma Cluster contain several enormous elliptical galaxies, each one a vast collection of hundreds of billions of ancient stars bound together by their collective gravitational attraction. These giant ellipticals represent the end stages of galactic evolution, formed through repeated mergers of smaller galaxies over billions of years as gravity drew matter together into increasingly massive structures. The largest of these central galaxies contains perhaps 1 trillion stars or more, a stellar city that dwarfs our own Milky Way, despite occupying a volume of space not dramatically larger than our home galaxy's extent. These giants dominate their surroundings gravitationally. One particularly notable galaxy in the Norma Cluster region carries the designation ESO 137001, a code referencing its entry in the European Southern Observatory catalogue of Southern Hemisphere objects. This galaxy shows dramatic evidence of interaction with the cluster environment, streamers of gas and dust trailing behind it as it plunges through the hot medium that fills the space between cluster galaxies. The stripping of material from galaxies as they fall into clusters represents one of the processes that transformed the cluster population from actively star-forming spirals into the quiet ellipticals that now dominate the central regions. The Norma cluster is an active environment despite its ancient age. The mass of the Norma cluster represents a significant fraction of what is needed to explain the cosmic flow that draws our region of space toward this direction, though estimates vary depending on the techniques used to measure the total gravitational influence. Early calculations suggested the cluster might contain mass equivalent to 1,000 trillion suns, roughly 10,000 times the mass of a galaxy like the Milky Way, concentrated into a relatively small volume. This enormous mass creates a gravitational well that influences the motion of everything within hundreds of millions of light years, contributing substantially to the pull we experience as part of the cosmic flow. The cluster acts as a gravitational anchor for its region of space. The hot gas filling the Norma cluster represents one of the most direct indicators of the cluster's enormous mass. Heated to temperatures of tens of millions of degrees by the gravitational energy released as it fell into the cluster's gravitational well. This gas was originally part of the galaxies themselves, or the intergalactic medium between them. But the cluster's gravity accelerated it to such high velocities that collisions between gas particles converted the kinetic energy into thermal energy. The result is a diffuse glow visible in X-ray observations, a bubble of superheated material that fills the space between the cluster's galaxies. The amount of gas and its temperature provide clues to the total mass required to create and maintain such extreme conditions. The distribution of galaxies within the Norma cluster shows the characteristic structure seen in massive clusters throughout the universe, with a dense core of giant ellipticals surrounded by less concentrated regions containing a mix of galaxy types. The core represents the bottom of the gravitational well, the region where matter has had the longest time to accumulate, and where the most extreme processes of galactic transformation have occurred. Moving outward from the core, the density of galaxies decreases gradually, blending eventually into the general field population that fills the space between major clusters. The boundaries of clusters are not sharp edges, but gradual transitions. The Norma cluster does not exist in isolation, but rather forms part of a larger structure of galaxies and clusters stretched across a vast region of space. This larger structure, sometimes called the Norma Wall or the Great Attractor Wall, represents a concentration of matter that extends for hundreds of millions of light years across the sky. The wall concept captures the flattened nature of the distribution. Galaxies and clusters arranged more along 2 dimensions than uniformly through 3-dimensional space. Such walls represent typical features of large-scale cosmic structure, sheets of matter separating the great voids that occupy most of the universe's volume. Approaching the Norma cluster from our direction would reveal a gradual increase in the density of galaxies as you traveled from the relatively sparse local group toward the concentrated cluster environment. First would come individual galaxies scattered through the space between our neighborhood and the cluster, then loose groups and filaments pointing toward the main concentration. Finally, the cluster itself appearing as a wall of galaxies, spread across tens of millions of light-years. The experience would be one of entering increasingly crowded cosmic territory, the isolation of intergalactic space, giving way to the communal environment of a major cluster. This is the direction we are traveling. The light from galaxies in the Norma cluster has been traveling for over 200 million years to reach us, carrying information about conditions that existed when dinosaurs dominated the Earth, and the continents occupied very different positions than they do today. By the time this light arrives at our telescopes, the cluster has continued evolving, galaxies merging and gas cooling, and new generations of stars being born in whatever star-forming regions remain active. The image we observe represents the distant past of the cluster, not its current state, though the timescales of galactic evolution are so long that the differences over a mere 200 million years remain relatively modest. The Norma cluster represents the most obvious candidate for the core of the Great Attractor, the central concentration toward which the cosmic flow converges. Though the full picture of gravitational influence in our region of space involves additional structures that complicate this simple interpretation. Later discoveries would reveal even larger concentrations of mass lying behind the Norma region at greater distances, raising questions about whether the traditional Great Attractor should be considered the ultimate destination of our cosmic journey, or merely a waypoint on a longer voyage. The universe often proves more complex than initial observations suggest. The mapping of cosmic flows eventually revealed that the Norma cluster and its associated structures belonged to a far larger gravitational basin. A supercluster containing over 100,000 galaxies that astronomers named Laniakea in 2014. This Hawaiian name, meaning immense heaven, captures something of the vast scale of a structure spanning more than 500 million light-years across the sky. Within this immense heaven, galaxies flow toward a common gravitational center, like streams flowing toward a drainage basin. Their motions defining the boundaries of the supercluster more clearly than any visible concentration of mass. The Great Attractor lies near the center of Laniakea, the gravitational heart around which everything orbits. The concept of a supercluster emerged from observations showing that galaxy clusters themselves are not uniformly distributed through space, but rather gather into larger associations, separated by enormous voids containing few galaxies at all. These superclusters represent the largest gravitationally bound structures in the universe, the maximum scale at which matter has had time to gather together under the influence of gravity since the universe began. On larger scales still, the expansion of space overwhelms the attractive force of gravity, preventing structures from collapsing into coherent units. Laniakea approaches this cosmic limit. The Milky Way occupies a position in the outer reaches of Laniakea, far from the gravitational center, where the Norma region and associated structures concentrate much of the supercluster's mass. Our cosmic neighborhood, the local group containing the Milky Way and Andromeda, and a few dozen smaller companions, participates in the flow toward this center, along with all the other galaxies spread across Laniakea's vast extent. The flow is slow by cosmic standards, 600 kilometers per second, representing a gentle drift when measured against the hundreds of millions of light-years that separate us from the central regions. The journey toward the center will require billions of years. The boundary of Laniakea was defined not by any visible edge, but by the concept of a watershed, the line separating regions that flow toward different gravitational centers. Just as rainfall on one side of a mountain ridge flows toward one ocean, while rainfall on the other side flows toward a different ocean, galaxies, on one side of the Laniakea boundary, flow toward our supercluster's center, while galaxies on the other side flow toward other gravitational concentrations. The boundary represents a balance point where the gravitational influences of different regions cancel each other, leaving galaxies on the boundary moving primarily with the general expansion of the universe rather than toward any particular attractor. The Virgo Cluster, the nearest large concentration of galaxies to our local group, at roughly 50 million light-years away, lies within Laniakea and participates in the same general flow toward the Great Attractor region. This cluster, containing over 1,000 galaxies visible from Earth in the northern sky, represents a significant mass concentration in its own right, influencing the motions of everything in its vicinity, including our own galaxy. The Milky Way falls toward Virgo, even as both Virgo and the Milky Way fall together toward the more distant Great Attractor. These nested flows create a complex pattern of motion through space. The Centaurus cluster and the Hydra cluster also belong to Laniakea, their names reflecting the constellations in whose directions they appear from our position on Earth. These massive gatherings of galaxies contribute their gravitational influence to the overall flow pattern, pulling on everything around them, while themselves being pulled toward the even more massive concentrations at the supercluster's heart. The architecture of Laniakea involves multiple nodes and filaments of concentrated mass connected by streams of galaxies flowing between them. We are embedded within this architecture, participants in its gravitational dynamics. The three-dimensional structure of Laniakea reveals itself through careful mapping of galaxy positions and velocities, the flow patterns indicating which regions are gravitationally connected and which belong to separate superclusters. The mapping project that defined and named Laniakea used data from thousands of galaxies, measuring their distances and velocities to reconstruct the gravitational landscape that shapes motion across this vast region. The result was a map showing our supercluster as a distinct entity, separated from neighboring superclusters like Perseus Pisces by boundaries where the flow patterns diverge. Our cosmic address finally had a clear definition at the largest scales. The name Laniakea was chosen by the research team led by Brent Tully to honor the Hawaiian tradition of navigation and wayfinding, appropriate for a discovery about our path through the cosmos, made in part using observations from Hawaiian mountaintops. The name also reflects the immense scale of the structure, a heaven so vast that light requires over 500 million years to cross from one edge to the other. Within this immense heaven, everything moves together in the slow gravitational dance that will continue for billions of years into the future. We are members of Laniakea, our address in the largest structures of the universe. The discovery of Laniakea's extent and boundaries changed the context in which astronomers understood the Great Attractor, revealing it as the gravitational center of a supercluster, rather than an isolated anomaly in the otherwise smooth cosmic expansion. Other superclusters throughout the universe presumably have their own great attractors, central regions toward which their member galaxies flow, under the influence of concentrated mass. The pattern we observe locally repeats itself across the cosmos. The same physics of gravitation creating similar structures wherever matter has had time to accumulate into concentrated regions. Our Great Attractor is not unique, but exemplary. The motion toward the Great Attractor that first alerted astronomers to the existence of this phenomenon now appears as part of the larger flow pattern within Laniakea. Galaxies throughout the supercluster participating in similar motions toward the common gravitational center. The 600 kilometers per second that carries us through space represents our particular contribution to this general flow. Our position in the outer reaches determining our specific velocity and direction. Galaxies closer to the center move differently, while galaxies on the far side of Laniakea from us flow from directions opposite to ours. The whole system moves together while its internal flows converge. Laniakea will continue evolving as gravity draws its member galaxies closer to the center. The supercluster gradually contracting under its own gravitational attraction, even as the universe around it continues expanding. This contraction happens slowly, competing against the cosmic expansion that tries to carry everything apart. The outcome depending on the precise balance between internal gravity and external expansion, in ways that remain subjects of ongoing research. The far future may see Laniakea merging into a single enormous galaxy, or it may see the supercluster stretching apart as expansion eventually dominates. The timescales involved exceed any human comprehension. The visible galaxies that trace the structure of Laniakea and define the Great Attractor region represent only a small fraction of the matter responsible for the gravitational attraction we experience as we flow through space. Most of the mass that pulls us toward the center of our supercluster consists of something we cannot see directly, a mysterious substance that astronomers call dark matter, because it neither emits nor absorbs any form of light. This invisible component outweighs the visible stars and gas by roughly 5-to-1, meaning that for every kilogram of normal matter in the universe, 5 kilograms of dark matter exist in forms we can detect only through gravitational effects. The Great Attractor's pull comes primarily from this unseen source. The existence of dark matter was first suggested by observations showing that galaxies and galaxy clusters contain far more mass than the visible stars and gas can account for. Stars at the outer edges of galaxies orbit faster than they should based on the gravitational pull of the visible matter within, suggesting additional unseen mass extending far beyond the luminous regions. Galaxy clusters hold together despite appearing to lack sufficient visible mass to prevent their member galaxies from flying apart. The motion of galaxies through superclusters, like Laniakea, requires far more mass than the visible concentrations can provide. Dark matter provides the missing gravity. The nature of dark matter remains one of the great unsolved problems in modern physics, the substance refusing to reveal itself through any interaction other than gravitation. Experiments designed to detect dark matter particles directly have so far produced null results, setting limits on what forms the substance might take without positively identifying its composition. Theoretical physicists have proposed numerous candidates, from hypothetical particles with exotic properties to modifications of our understanding of gravity itself. But no definitive evidence has emerged to confirm any particular proposal. The dark matter that dominates the mass of the Great Attractor remains genuinely mysterious. What we do know about dark matter comes primarily from its gravitational effects, which can be mapped through several independent techniques that all yield consistent results. The motions of galaxies within clusters reveal how much total mass binds them together, exceeding the visible mass by large factors. The bending of light from distant sources as it passes through massive structures reveals the distribution of total mass, regardless of whether that mass emits light. The growth of structure throughout cosmic history depends on the total amount of matter available to clump together under gravity. All these measurements converge on the same answer: most matter is dark. The dark matter associated with the Great Attractor exists as enormous halos surrounding and interpenetrating the visible galaxy clusters, extending far beyond the luminous cores into the intergalactic space between major structures. These halos formed first in the early universe, condensing from tiny density fluctuations present shortly after the beginning of everything, while normal matter was still too hot to collapse. The dark matter halos then served as gravitational scaffolding, drawing in normal matter that eventually cooled, condensed, and formed the visible galaxies we observe today. The pattern of visible galaxies traces the underlying dark matter distribution. The gravitational pull drawing us toward the Great Attractor thus comes primarily from dark matter concentrations that we cannot photograph or observe directly. Invisible wells of mass that shape the motions of everything in their vicinity. The Norma cluster and other visible structures mark the locations where dark matter halos are densest, the visible galaxies serving as tracers of the underlying gravitational landscape, rather than as the source of that gravity themselves. When we speak of falling toward the Great Attractor, we are really falling toward an enormous concentration of dark matter that happens to contain visible galaxies as a minority component. The concept of invisible matter shaping visible motions may seem strange from the perspective of everyday experience, where the things that affect us are usually the things we can see and touch. Yet gravity operates without regard to visibility, pulling equally on all forms of matter, whether luminous or dark, massive or sparse, nearby or distant. The dark matter filling the Great Attractor region pulls on our galaxy exactly as visible matter would, the force depending only on mass and distance, without any consideration of whether photons connect us to the source. We are drawn by something we cannot see, because gravity does not require visibility. The distribution of dark matter throughout the universe follows a characteristic pattern that simulations predict based on the physics of gravitational collapse operating over billions of years. Dense concentrations form at the intersections of filaments, with less dense regions along the filaments themselves, and nearly empty voids occupying most of the cosmic volume. This pattern, called the cosmic web, consists primarily of dark matter, with visible galaxies following along as tracers of the underlying structure. The Great Attractor represents one node in this cosmic web, a place where multiple filaments converge and dark matter has accumulated to exceptional density. The relationship between dark matter and normal matter in the Great Attractor region follows the same ratio observed throughout the universe, approximately 5:1 in favor of the invisible component. This ratio was established in the first moments after the universe began, when the processes that created matter produced dark matter and normal matter in these fixed proportions. Every structure we observe contains both components in this ratio, from individual galaxies to galaxy clusters to superclusters like Laniakea. The Great Attractor is no exception. Its gravitational pull, dominated by the dark matter that lurks invisibly among the luminous galaxies we can photograph. The journey we are taking toward the Great Attractor is thus a journey toward an invisible destination. The dark matter that comprises most of the attractive mass, remaining hidden behind its refusal to interact with light. We can see the galaxies that mark the location of this mass concentration, but the mass itself remains imperceptible to any form of electromagnetic observation. The Great Attractor attracts through gravity, not through light, and the gravity comes primarily from matter that shares this same relationship with the electromagnetic spectrum. We are drawn by what we cannot see toward what we cannot see. The mystery of dark matter adds a philosophical dimension to our cosmic journey. The realization that most of what shapes our motion through the universe remains fundamentally unknown to us, despite decades of investigation. We know dark matter exists because its effects are undeniable. Yet we do not know what it is or why it exists in the quantities we observe. The Great Attractor represents this mystery in concrete form, a real gravitational influence on our real motion through space, created primarily by a substance whose nature remains hidden. The universe contains more than we can see. As astronomers continued mapping the cosmic flows at ever larger scales, they discovered evidence that the Great Attractor itself might be moving, drawn toward an even more massive concentration of matter, located farther away in the same general direction. This larger structure, called the Shapley concentration, or Shapley supercluster, lies roughly 650 million light-years from the Milky Way, approximately 3 times the distance to the Norma cluster that defines the traditional Great Attractor. The Shapley concentration contains dozens of galaxy clusters packed into a relatively small volume, creating a gravitational well that may dominate the motion of our entire region of space. The ultimate attractor might be farther away than originally thought. The Shapley concentration was named for Harlow Shapley, an American astronomer who made important contributions to understanding the scale and structure of the universe in the early 20th century. Shapley himself did not recognize the significance of this particular concentration of galaxies, which would not be appreciated until decades after his observations, when large-scale surveys revealed its exceptional density relative to surrounding regions. The structure contains at least 8 massive galaxy clusters within a volume of space that would normally be expected to contain perhaps 1 or 2 such clusters, an overdensity that makes it one of the most massive structures in the observable universe. The mass of the Shapley concentration has been estimated at roughly 4 to 5 times the mass of the traditional Great Attractor region, a gravitational influence so enormous that it should affect motions across billions of light-years of surrounding space. At its greater distance from us, this mass produces a gravitational pull that compounds with the pull of the Norma region, both structures contributing to the cosmic flow that carries our galaxy through the darkness. Some astronomers now argue that the Shapley concentration is the true attractor, the ultimate destination of our cosmic journey, with the traditional Great Attractor serving as an intermediate waypoint along a longer path. The question of which structure dominates our motion remains an active area of research and debate. The relationship between the Great Attractor and the Shapley concentration resembles a hierarchy of gravitational influence, with smaller structures nested within larger ones in a pattern that repeats across many scales of cosmic architecture. Our local group falls towards the Virgo Cluster, while the local group and Virgo together fall towards the Great Attractor region, while everything in this vicinity may be falling together toward the even more massive Shapley concentration beyond. This nested flow creates complexity in the motion of individual galaxies, their velocities reflecting the combined pull of multiple attractors at different distances and in slightly different directions. The cosmic journey involves multiple destinations arranged in sequence across hundreds of millions of light years. The cluster cores within the Shapley concentration glow brightly in X-ray observations, their hot intergalactic gas revealing the enormous masses required to heat these vast volumes to temperatures of tens of millions of degrees. The X-ray emission allows astronomers to estimate the total mass of each cluster, including the dark matter that dominates but remains invisible to other forms of electromagnetic observation. The accumulated mass across all the clusters in the concentration reaches values almost incomprehensible in everyday terms, equivalent to perhaps 50,000 trillion suns gathered into this single region. This mass creates the gravitational well that may be the ultimate destination of our cosmic flow. Approaching the Shapley concentration from our direction would reveal an even more dramatic increase in galaxy density than approaching the Norma region. The clustering of massive structures creating a cosmic overdensity visible across enormous volumes of surrounding space. The multiple galaxy clusters would appear as separate concentrations at first, gradually merging into a connected complex as distances decreased and the individual structures blended together visually. The experience would be one of entering the most crowded neighborhood in the observable universe, a gathering of matter that represents an extreme example of what cosmic structure formation can produce. This is the direction we are traveling, though arrival lies billions of years in the future. The debate about whether the Great Attractor or the Shapley concentration serves as the primary source of our cosmic flow continues among specialists who study large-scale structure and galaxy dynamics. The answer depends partly on definitions, on how one chooses to draw boundaries between different concentrations of mass, and how one allocates responsibility for observed motions among multiple contributing sources. Both structures clearly contribute to the gravitational field that accelerates our region of space, their combined influence creating the flow pattern that carries over 100,000 galaxies toward a common, general direction. The ultimate attractor may be both structures working together, or something even larger that encompasses them both. The possibility that even larger structures might be influencing our motion has led some astronomers to search for additional concentrations at distances beyond the Shapley region. Gravitational influences that might contribute to flow patterns at the most distant observable scales. These searches are complicated by the difficulty of measuring accurate distances and velocities for extremely remote galaxies. The subtle signatures of peculiar motion becoming harder to distinguish from measurement uncertainties as distances increase. The question of where our cosmic journey ultimately leads remains open at the most distant scales, the universe potentially containing structures we have not yet detected or characterized. The journey may extend farther than current observations can trace. The timescales involved in reaching either the Great Attractor or the Shapley concentration stretch into billions of years, spans of time so long that predictions about endpoints become somewhat abstract exercises in cosmic geometry. At our current velocity of 600 kilometers per second, reaching the traditional Great Attractor would require several 100 million years of continuous travel through intergalactic space. Reaching the more distant Shapley concentration would require over 1 billion years of this same steady motion, during which the galaxies themselves will change dramatically through internal evolution and interactions. The end point of the journey may involve a very different galaxy than the one currently carrying us through the darkness. The nested hierarchy of gravitational attraction, revealed by the Shapley concentration, suggests a universe organized across many scales, with structures at each level influencing the motion of everything within them, while themselves being influenced by larger structures surrounding them at greater distances. This organization emerges naturally from gravity acting over billions of years. Small initial variations in density growing into the elaborate cosmic web we observe today, stretched across the observable universe. The Great Attractor and Shapley concentration represent nodes in this web, places where matter accumulated more effectively than average in the early universe, and now dominates the gravitational landscape of their respective regions. We are embedded within this hierarchy at a particular location that determines our specific trajectory. The view toward the Shapley concentration from our current position would reveal layer upon layer of galaxy clusters receding into the distance, each layer representing additional mass contributing to the gravitational pull we experience here in the outer reaches of this vast structure. The nearest clusters would show individual galaxies, ellipticals and spirals caught in their dense environments, while more distant clusters would blend into concentrated glows, marking their positions across hundreds of millions of light years. The entire structure extends across a volume that light requires hundreds of millions of years to cross, a gathering of matter so large that its full extent challenges visualization, even in the abstract. This is what lies in the direction we are traveling, whether our ultimate destination is the Norma region, the Shapley concentration, or something beyond that we have not yet mapped. The journey continues unchanged by our knowledge or ignorance of its eventual endpoint. The gravitational pull that accelerates our galaxy operates regardless of whether we understand its source, the physics of attraction caring nothing for human comprehension or attention. We are passengers on a journey that will outlast our species, carried toward destinations we may never fully map or understand, despite our best efforts to observe and calculate. The cosmos moves through itself in the darkness, and we move with it toward whatever waits ahead. The experience of contemplating these nested structures and their gravitational relationships offers a particular perspective on our place in the cosmic order, embedded within hierarchies that extend from stellar systems to superclusters across many orders of magnitude in scale. At each level, gravity organizes matter into structures that participate in larger patterns at the next level up. The whole cosmos, arranged in this nested fashion, from planets orbiting stars to galaxies falling towards superclusters. The Great Attractor and Shapley concentration represent our local portion of this universal pattern, the specific structures toward which our region of the cosmic web flows under gravitational influence. The pattern repeats throughout the observable universe, wherever we look with sufficient care. The future may reveal even larger structures beyond the Shapley concentration. Additional concentrations at greater distances that contribute their own gravitational influence to the cosmic flows we observe and participate in locally. Each improvement in observational capability has revealed additional complexity in the distribution of matter across the universe. the cosmic web proving more intricate with each deeper survey of galaxy positions and motions. The catalogue of great attractors will likely grow as technology improves, each edition providing new context for understanding the flows that carry everything through the darkness. The universe contains more structure than any generation of astronomers has fully mapped. The cosmic journey carrying us toward the Great Attractor has been underway since the Milky Way formed over 13 billion years ago. Our galaxy, participating in gravitational flows from its earliest moments of existence as a coherent structure. The concentrations we now recognize as the Great Attractor and Shapley concentration have been pulling on our region of space since those ancient times, when the universe was still young and the first stars were only beginning to form in the primordial darkness. The journey will continue for billions of years into the future, long after our sun has exhausted its fuel and the Earth has become uninhabitable by anything resembling current life. We observe a moment in a voyage almost impossibly longer than human timescales can meaningfully represent. The speed of our motion, 600 kilometers per second, sounds impressive when stated in human terms of velocity and distance, but represents a gentle drift when measured against cosmic distances and the timescales required to traverse them. At this velocity, the Milky Way travels roughly 20 billion kilometers in a single year, a distance that would carry you across our solar system several times over, from edge to edge. Yet the Great Attractor lies over 200 million light-years away, a distance so vast that even at our remarkable speed, measurable progress requires millions of years to accumulate into anything significant. The cosmos operates with patience that no human culture has ever attempted to match in any of its undertakings. The path of our galaxy through space, over the past 13 billion years, would trace an enormous curve through the darkness. The accumulated distance traveled at 600 kilometers per second, adding up to something almost incomprehensible when multiplied across the full age of our stellar home. Every second since the Milky Way formed, another 600 kilometers of progress toward the current direction of flow has accumulated into the vast journey we continue today. The direction itself has shifted as the gravitational landscape evolved and the concentrations we now call the Great Attractor assembled from smaller precursor structures over cosmic time. The journey has been continuous, but the destination has changed as structures formed and grew. In the far future, the Milky Way will merge with the Andromeda Galaxy, the two spiral structures combining into a single larger galaxy. Over the course of several billion years of gravitational interaction and stellar mixing, this merger will occur while both galaxies continue their journey toward the Great Attractor, the combined system inheriting the momentum of both previous galaxies and continuing the flow that began when each existed as a separate structure. Astronomers sometimes call the future merged galaxy Milkomeda or Milkdromeda, names reflecting its dual origins in two formerly independent spiral galaxies, approaching each other across intergalactic space. This merged galaxy will still be falling toward the Great Attractor long after the merger completes. The Sun will exhaust its hydrogen fuel and swell into a red giant in roughly 5 billion years, eventually shedding its outer layers and leaving behind a dense white dwarf that will cool slowly over timescales exceeding the current age of the universe. This transformation will occur while the solar system continues its journey within the Milky Way, which continues its journey within the local group, which continues its journey toward the Great Attractor region. The human timescale and the cosmic timescale exist in such different ranges that the former becomes essentially instantaneous when measured against the latter, our entire species existing for barely a flicker in cosmic terms. The journey proceeds on timescales that dwarf everything humans consider ancient or enduring. The destination of our cosmic journey remains uncertain in several important respects. The ultimate endpoint depending on factors that remain difficult to predict, even with our best current understanding of cosmic dynamics and evolution. The expansion of the universe competes against gravitational attraction at the largest scales, with expansion eventually overwhelming gravity for sufficiently distant regions that are separating faster than they are falling together. Whether the structures we are falling toward will remain accessible or will be carried away by expansion depends on details of the cosmic expansion history that observations continue to refine. The journey may not have a reachable endpoint if expansion accelerates sufficiently. If the cosmic expansion were to accelerate sufficiently in the future, the gravitational bonds holding Laniakea together might eventually break, the supercluster stretching and thinning as expansion overcomes attraction across its enormous extent. Observations suggest that such acceleration is indeed occurring, driven by an unknown form of energy that fills empty space and pushes against gravitational contraction with increasing strength as time passes. This dark energy, even more mysterious than dark matter, may eventually isolate the Milky Way from all the structures toward which we currently fall through cosmic space. The journey might continue forever, without ever arriving at any destination if expansion eventually dominates over attraction. The timescale on which such cosmic changes might occur extends far beyond anything directly relevant to human concerns. Tens of billions of years into a future that will find no trace of our current civilization remaining in any recognizable form. The journey toward the Great Attractor will outlast human history by factors so large that comparison becomes meaningless. The cosmic voyage continuing through eras we cannot imagine in any detail, despite our best efforts at extrapolation. Our participation in this journey connects us to timescales that dwarf individual lives, civilizations, and even species by margins that challenge any attempt at meaningful comprehension. We exist for an instant within an eternal flow. The present moment in this journey carries no particular significance from the cosmic perspective. Just another instant in a flow that has continued for billions of years and will continue for billions more, regardless of what happens on any particular planet orbiting any particular star. We happen to exist during this instant, conscious beings capable of recognizing the journey and contemplating its meaning, wondering about destinations and timescales, and our place within structures almost too large to visualize. This awareness adds nothing to the physics of gravitational attraction, but adds everything to the human experience of being embedded in such vast patterns. We are passengers who have noticed the vessel is moving through the darkness. The accumulation of astronomical knowledge that allows us to recognize our cosmic journey represents a remarkable achievement of human curiosity and ingenuity. Generations of observers and theorists building understanding across centuries of patient effort and careful observation. The astronomers who first detected our peculiar velocity, who named the Great Attractor and mapped the Zone of Avoidance, and revealed the Shapley concentration, contributed to a picture of cosmic structure that their predecessors could not have imagined in even their most speculative moments. The journey has been underway since the universe was young, but we have only recently noticed that we are traveling through something much larger than our immediate surroundings suggested. This recognition changes nothing about the physics of our situation, but changes everything about how we might experience our place in the universe and understand our relationship to the structures that surround us. We are not stationary observers watching the cosmos from a fixed position, but rather participants in its ongoing evolution, carried along by forces that operate at the largest scales nature has produced anywhere in the observable universe. The Great Attractor waits in the distance, pulling on everything within its gravitational reach, and we are among the things being pulled towards its concentrated mass. The journey continues whether we attend to it or not. The view from our moving platform would show nothing of the motion if we could somehow perceive only the relative positions of nearby objects. The entire local group traveling together with velocities so similar that no internal motion reveals the cosmic drift we share. Only by looking outward to distant galaxies in different directions do we detect the asymmetry in their apparent motions that reveals our own velocity through the cosmic reference frame. The method of detection reminds us that motion is always relative, that our velocity exists only in comparison to other objects against which we measure our changing position. The Great Attractor provides one such reference, the direction toward which we move and from which we measure our approach. The emotional or philosophical significance of this cosmic journey varies depending on how one chooses to relate to the scale and timescale of the structures involved in carrying us through the universe. Some may find comfort in being embedded in something so vast, the individual concerns of human life contextualized within a grander pattern that extends far beyond anything we can directly influence or alter. Others may find the scale alienating, the human experience seeming small against the backdrop of superclusters and billions of years of patient gravitational drift through darkness. The cosmos offers no guidance on how to feel about our position within it. The Great Attractor and Shapley concentration exist not as isolated features in an otherwise empty or uniform cosmos, but as nodes in the cosmic web, the vast network of filaments and voids that organizes matter at the largest scales throughout the entire observable universe. This web-like structure emerged from tiny density fluctuations present in the very early universe, infinitesimal variations in the distribution of matter that gravity amplified over billions of years into the enormous structures we observe today, scattered across all directions of the sky. The same physics that created the Great Attractor created similar structures throughout the cosmos. The pattern of clustering and flowing, repeating wherever matter has had time to accumulate under gravitational influence. Our local structures represent one example of a universal phenomenon. The cosmic web consists of three main components arranged in a characteristic pattern that computer simulations reproduce with remarkable fidelity when the underlying physics is correctly specified and applied across cosmic timescales. Dense concentrations of matter form at nodes where multiple filaments intersect. These nodes hosting the massive galaxy clusters and superclusters that dominate their respective regions of surrounding space. Thinner filaments of matter stretch between the nodes, containing individual galaxies and smaller groups flowing toward the nearest node along gravitationally defined paths. Vast voids occupy most of the cosmic volume, nearly empty regions where matter has drained away toward the surrounding filaments and nodes over billions of years of gravitational evolution. The filaments of the cosmic web can stretch for hundreds of millions of light years. Threads of gravitationally connected matter linking distant nodes across volumes almost too large to visualize in any meaningful way. Galaxies within these filaments flow along their lengths toward the nodes at either end. Participating in the general gravitational drainage that concentrates matter at the intersections where filaments meet and merge. The Milky Way sits within one such filament, flowing toward the node we call the Great Attractor, along with all our cosmic neighbors throughout the local group and beyond. The flow pattern we experience locally represents a small portion of a structure that extends throughout the observable universe. The voids between filaments can span hundreds of millions of light years across, enormous volumes containing very few galaxies compared to the cosmic average that characterizes denser regions where structures have formed effectively. These voids are not truly empty, but merely underdense, containing scattered galaxies that failed to accumulate into the denser regions during cosmic evolution, when matter was sorting itself under gravitational influence. The contrast between void and filament creates the web-like appearance when the distribution of galaxies is mapped across large volumes using survey data accumulated over years of observation. The Great Attractor region represents one of the densest concentrations, surrounded by less dense regions that have contributed their matter to the central accumulation. The formation of the cosmic web can be understood as gravity acting on the tiny initial variations in density that existed shortly after the universe began, amplifying these variations over billions of years into the dramatic contrasts we observe today across all observable space. Regions slightly denser than average attracted additional matter, growing denser still, while surrounding regions lost matter and became relatively emptier over cosmic timescales. This feedback process, called gravitational instability, operates everywhere throughout the universe, but produces different specific results depending on the initial conditions that happen to exist in each particular region. The Great Attractor formed where initial overdensities happen to be larger than the cosmic average. The dark matter that dominates the mass of the universe plays the primary role in building the cosmic web, its particles clustering under gravity, without the complicating effects that radiation pressure and other forces exert on normal matter during the early universe. The dark matter web formed first, creating the gravitational scaffolding into which normal matter later fell as the universe cooled and expanded beyond the point where radiation pressure could prevent gravitational collapse. The visible galaxies we observe trace this underlying dark matter distribution, markers of structure that remains otherwise invisible to all our instruments, regardless of wavelength. The cosmic web consists primarily of dark matter, with galaxies serving as luminous tracers of the deeper invisible structure. The scale of the cosmic web challenges human intuition about size and distance. The structures spanning volumes so vast that light requires billions of years to cross from one side to the other. The observable universe contains countless such structures, overlapping and interpenetrating in a complex three-dimensional pattern that simulations can reproduce, but that direct visualization struggles to capture in any intuitive way. The Great Attractor represents one small portion of this universal pattern. Significant to us because we happen to be falling toward it, but similar in nature to countless other nodes scattered throughout the entire cosmos. We observe our local example of something universal. The flows within the cosmic web carry galaxies along the filaments toward the nodes, draining matter from the voids and concentrating it at the intersections where gravity is strongest and where the largest structures have formed. These flows happen slowly by human standards, but represent enormous motions when accumulated over cosmic timescales. The redistribution of matter across billions of light years, driven by the patient work of gravitational attraction operating without rest or interruption. The flow we experience toward the Great Attractor represents our participation in this universal drainage, our contribution to the continuing evolution of cosmic structure on the largest scales. We are part of something that encompasses the entire observable universe. The future evolution of the cosmic web depends on the competition between gravitational attraction and cosmic expansion, with expansion eventually dominating at the largest scales, while gravity maintains coherent structures at smaller scales where mass concentrations are sufficient. The Great Attractor will likely remain a coherent node for billions of years, continuing to draw in surrounding matter while the universe expands around it at ever-increasing rates. The ultimate fate of such structures over timescales of trillions of years remains uncertain. The very long-term future of the cosmos, less well understood than the processes operating in the current epoch. Expansion may eventually stretch the web beyond recognition. The understanding of the cosmic web provides context for appreciating the Great Attractor as a natural consequence of universal physics, rather than as an anomaly requiring special explanation or unusual conditions to produce. The same gravitational processes that built structures throughout the observable universe built the concentration toward which we fall. The same dark matter halos and galaxy clusters and superclusters that appear wherever we point our telescopes with sufficient sensitivity and patience. Our Great Attractor is not unique, but typical, one node among countless others in the universal web of matter that defines cosmic structure everywhere. The pattern we participate in locally repeats throughout all observable space. The experience of being embedded in this web, of flowing along its filaments toward its nodes, connects us to the largest structures the universe has produced through billions of years of gravitational evolution from nearly uniform initial conditions. We are not observers standing outside the cosmos, but participants within it. Our motion through space reflecting the gravitational forces that have shaped everything since matter first began clustering in the young universe, shortly after the beginning. The cosmic web surrounds us and includes us. Our journey toward the Great Attractor, representing our local expression of a pattern that extends throughout all the space we can observe. We belong to something vast. The visualization of our position within the cosmic web reveals the Milky Way as a tiny speck within an enormous filament, flowing toward a node that itself represents just one concentration among countless. Others scattered across the observable universe in all directions. The scale dwarfs any structure humans have ever built or imagined, the web extending beyond the limits of observation into regions we may never be able to characterize, regardless of how our technology develops. Yet we are part of this structure, embedded within it, participating in its flows and contributing our tiny mass to its gravitational dynamics. The cosmic web is our home at the largest scale. The Great Attractor represents our local example of a phenomenon that repeats throughout the observable universe. Each region of space experiencing similar gravitational flows toward its own massive concentrations of matter along its own particular trajectory. Observers in distant galaxies would find themselves participating in their own cosmic journeys, falling toward their own great attractors, along with all their galactic neighbors in flows similar to ours. The pattern we observe locally is universal. The same physics operating everywhere to produce similar results wherever matter has accumulated into dense concentrations over billions of years of gravitational evolution. We are not special in our motion, but exemplary of cosmic behavior. Surveys mapping the distribution of galaxies across enormous volumes have revealed numerous great walls and superclusters comparable to or larger than the structures in our local region of space that influence our motion. The Sloan Great Wall, detected in data from the Sloan Digital Sky Survey, stretches approximately 1.37 billion light-years across the northern sky as viewed from Earth. This structure is so large that it challenges assumptions about the maximum size of coherent cosmic features, raising questions about whether even larger structures might exist beyond current observational limits. Other structures of comparable or greater extent appear elsewhere in the surveys, suggesting that the universe contains many nodes, rivaling or exceeding our local attractors. The Hercules Corona Borealis Great Wall may be the largest known structure in the observable universe, a concentration of mass spanning roughly 10 billion light-years across a region of distant space far beyond our local cosmic neighborhood. This structure, detected through observations of gamma-ray bursts originating from massive stellar explosions within it, remains poorly characterized due to its enormous distance and the limitations of currently available observation techniques. If confirmed at its estimated size, it would exceed anything else known in terms of sheer spatial extent, though its total mass and gravitational influence remain uncertain pending better observations. The universe may contain structures even larger than this. These distant structures host their own cosmic flows, galaxies streaming towards central concentrations, just as our region streams toward the Great Attractor and Shapley concentration at 600 kilometers per second. Observers within those distant regions would measure their own peculiar velocities, detect their own asymmetries in the cosmic microwave background radiation, and map their own zones of avoidance created by whatever galaxy hosted their hypothetical astronomical observatories, looking outward at their surrounding cosmos. The universal physics of gravitation creates universal patterns of structure and motion. The Great Attractor representing our local instantiation of something common throughout all observable space. The repetition of similar structures across the observable universe reflects the homogeneity of cosmic initial conditions. The tiny density variations present in the early universe, showing the same statistical properties everywhere, rather than clustering in particular privileged regions. Gravity amplified these variations equally everywhere, producing similar structures across all observable space, given similar starting conditions in different regions. The Great Attractor formed from slightly overdense initial regions, and similar overdense regions existed throughout the early universe in all directions, producing similar attractors throughout the present cosmos. Wherever we care to look, the pattern is universal. The flows toward different attractors do not interact directly in most cases, the structures being separated by such vast distances that their gravitational influences barely overlap with each other across the intervening space. Galaxies falling toward the Great Attractor are not significantly affected by the gravitational pull of distant structures like the Sloan Great Wall, the cosmic expansion, ensuring that these structures recede from each other faster than their gravity can draw them together across such enormous separations. Each attractor dominates its local region while remaining essentially independent of distant attractors occupying their own cosmic neighborhoods. The independence of different gravitational domains creates a cosmic landscape of separate watersheds, each supercluster representing a drainage basin where galaxies flow toward local gravitational centers rather than toward more distant concentrations in other regions. The boundaries between these watersheds define the edges of structures like Laniakea, the lines where flows toward different attractors balance each other, and galaxies move primarily with the cosmic expansion rather than toward any particular nearby concentration. Crossing such a boundary would mean leaving one gravitational domain and entering another with its own central attractor and its own flow patterns. The observation that similar structures exist throughout the universe raises philosophical questions about our place in the cosmos and the significance of our particular gravitational journey through it. We are not special in falling toward a massive concentration of matter, not unique in participating in cosmic flows, not alone in being embedded within the cosmic web's vast architecture that extends throughout all observable space. This ordinariness might be interpreted as diminishing or as connecting, depending on the perspective one chooses to bring to contemplating our situation. We share our fundamental circumstances with hypothetical observers throughout the universe. The universality of cosmic structure provides confidence that the physics we have developed to explain local phenomena applies equally throughout the observable universe. The same gravitational laws and dark matter properties and expansion history operating everywhere without variation or exception. This uniformity allows astronomers to use distant observations to constrain theories of cosmic evolution, comparing predictions against the full range of available data, rather than just local measurements that might reflect unusual conditions. The Great Attractor teaches us about universal physics while representing one particular location in the cosmos that happens to be relevant to our motion. The future may reveal additional great attractors and superclusters in regions of space currently beyond detailed observation. The universe, containing more structure than current surveys can map in complete detail, given the limitations of existing instruments. Each improvement in observational capability reveals additional complexity in the cosmic web, additional nodes and filaments and voids that populate the volumes between well-studied nearby regions and extend into the distance. The catalogue of great attractors will likely grow as technology improves and observations push deeper into the surrounding cosmos. The great attractor that influences our motion thus represents one entry in a cosmic inventory of similar structures. Notable to us because we are falling toward it, but similar in nature to countless others scattered across the observable universe in all directions. This perspective places our local structure within its proper context as typical rather than exceptional. One example of what gravity produces whenever it has billions of years to concentrate matter into the patterns we observe everywhere. The universe repeats itself at these largest scales, producing similar structures through similar processes, throughout all observable space, without apparent preference for any particular region. The recognition of this universality provides a kind of cosmic solidarity. The knowledge that our situation is shared by observers throughout the universe who find themselves embedded in similar structures and participating in similar flows towards similar concentrations of matter. We are all in this together. All the galaxies and all the hypothetical observers they might contain, all falling towards something, all participating in the gravitational organization of matter that has been underway since the universe was young. The Great Attractor is ours, but there are many like it, and they all reflect the same physics operating everywhere. The journey we have traced tonight continues at this moment and every moment, the Milky Way carrying us through space at 600 kilometers per second toward the concentrations of matter that define our cosmic neighborhood and shape our trajectory through the universe. Nothing about this motion will change appreciably during any human lifetime. The flow is constant and patient as gravity itself, operating across hundreds of millions of light years without rest or variation. We are embedded in something vast, participants in a motion that connects us to the largest structures the universe has produced through billions of years of gravitational evolution. The Great Attractor waits in the distance, drawing everything toward itself with an influence that has shaped cosmic structure since the universe was young. The motion happens without any sensation, without any perceptible change to the stars above or the ground beneath your current location. The journey so smooth that ordinary experience provides no hint of our velocity through the cosmic frame of reference. You could spend an entire lifetime attending carefully to the sky and never detect the drift that carries you 20 billion kilometers closer to the Great Attractor each year of your existence. The smoothness results from the vast distances involved. The gravitational gradient, so gentle across the scale of human experience, that differential forces remain essentially zero everywhere we might measure them. We fall freely through space, weightless in the cosmic sense, experiencing gravity only from nearby masses, like the Earth beneath us. The darkness above, wherever you rest tonight, contains the direction of our motion. The constellations in the southern sky, marking the region toward which everything flows together at hundreds of kilometers every second. The stars you see belong to the Milky Way, fellow travelers on this cosmic journey, their light providing no indication of the motion we share through the intergalactic darkness. Beyond those stars, hidden by the intervening dust and gas of our galaxy's disk, the Great Attractor region contains the mass concentrations that have been pulling us for billions of years of continuous travel. The destination hides behind the beauty of the Milky Way itself. The knowledge of this journey changes nothing about the physics of our situation, but adds a dimension to human experience of the cosmos that earlier generations entirely lacked. We know ourselves to be moving through the universe, participants in flows that extend across hundreds of millions of light years and connect us to structures almost incomprehensibly larger than anything our ancestors could have imagined when they looked up at the same stars. This knowledge represents an achievement of human curiosity, operating through generations of careful observation and theoretical development, building upon earlier work. The motion existed long before we discovered it, and will continue long after we are forgotten. The scale of the structures involved defies casual comprehension, requiring active effort to appreciate the meaning of numbers like 100,000 galaxies or 200 million light-years of distance, traversed over cosmic timescales. Each of those galaxies contains billions of stars, each star potentially hosting planets of its own in systems that have evolved for billions of years. We are falling toward all of this, carried along by gravity with everything around us, participants in a congregation of matter that will require billions of years to complete its assembly. The timescales involved make human concerns seem brief indeed by comparison. The peace of this cosmic motion offers a particular kind of comfort, the knowledge that we are embedded in something vastly larger than ourselves, carried along by forces that operate with sublime indifference to human affairs and concerns. The universe moves through itself, galaxies drifting through the darkness, matter accumulating under the patient work of gravity that never tires or rests. Our participation in this motion requires nothing of us, asks nothing from us, proceeds regardless of our attention or inattention to its presence. We are along for the ride. The journey will outlast everything familiar, continuing through eras that will find no trace of current civilization, no memory of the species that first detected this cosmic flow and wondered about its destination and meaning. The Milky Way will merge with Andromeda. The Sun will exhaust its fuel and expand into a red giant. The Earth will become uninhabitable. Yet the journey will continue uninterrupted through all these transformations. The gravitational pull of the Great Attractor operates on timescales that dwarf biological and geological time alike. The cosmos rearranging itself with patience that nothing human has ever demonstrated in any endeavor. The experience of resting while traveling, of being carried through space while lying still wherever you are tonight, creates a peculiar harmony between activity and passivity that the cosmos provides without requiring any effort or awareness on our part. You travel faster than any vehicle humans have ever built simply by existing, your position in the universe changing by thousands of kilometers in the time it takes to draw a single breath. This motion requires nothing from you, demands no attention or intention, proceeds as you sleep toward waking or wake toward sleep. The universe moves whether we attend to it or not. The Great Attractor represents something hidden that nonetheless shapes our path through existence, an influence we cannot see directly, but whose effects determine our trajectory through cosmic time and space. The parallel to many aspects of human experience seems striking. The recognition that unseen forces often shape our journeys in ways we only gradually come to understand through careful attention. The astronomical discovery of our cosmic motion provides a concrete example of such hidden influence, something real and measurable that was invisible until careful observation revealed its unmistakable presence. We are shaped by what we cannot see. The flow of 100,000 galaxies toward a common gravitational center happens in perfect silence, without any sound to mark the motion of these stellar cities through the void between them, across hundreds of millions of light years. The cosmos conducts its business without soundtrack, without the dramatic orchestration that human storytelling usually demands to convey significance and importance. The journey simply continues, moment after moment, kilometer after kilometer, year after year across billions of years of cosmic history and into billions more of cosmic future. The silence of space extends to the largest motions the universe contains. Tonight, as you rest wherever you are, the motion continues unchanged by your awareness or unawareness of its presence and direction. The Milky Way travels toward the Great Attractor at 600 kilometers per second, carrying with it the Sun and Earth and every living thing our planet hosts in its journey around our star. The journey has been underway since before life existed anywhere in our galaxy, and will continue long after life ends on worlds we will never know existed. We are participants in something vast, embedded in structures we can barely comprehend, moving through the cosmos toward destinations that will take billions of years to approach. The Great Attractor waits in the darkness, patient and invisible, drawing everything toward itself with gravity that has operated since the universe was young and matter first began gathering into the structures we now observe surrounding us in all directions. The journey continues as it has continued since that ancient beginning, the cosmos organizing itself into patterns we observe and participate in without perceiving through any direct sensation. 100,000 galaxies flow together through the darkness, moving toward a common destination across timescales that exceed any human ability to experience directly or comprehend intuitively. We drift among them, carried along by the same forces. The night continues, the motion continues, and sleep may come while the cosmos carries us forward through the endless dark towards something we cannot see, but that shapes our path through existence. The Great Attractor remains ahead, and the Shapley concentration beyond it, and the cosmic web stretching throughout all observable space, connecting everything in gravitational embrace. 100,000 galaxies move together, and we move with them, passengers on a journey that began before the Earth existed and will continue after the sun has faded into cooling silence. The universe drifts through itself, and we are part of the drifting, always moving, always traveling, always home within the flow.